goes. First, I want to give a shout out to, in particular, Anna Martins, a former student of mine, Matt Tam, and Tao Nguyen. What I'll be talking about is based on a lot of works, but most of the core of this was developed while Matt and Tao were here and together with them. So I want to give them a shout out for this. In the context of a lot of problems, Mark Tiboul and Shalom Sabach and I last year published sort of a numerical benchmarking paper that looked at cone and sphere problems, and so these types of problems motivated the theory that I was looking at, and so the basic problem is find a nearest point in some sense to a cone and to spheres in the image of affine transformations. And this covers in particular phase retrieval problem and source location. Both in particular phase retrieval is a problem that's been my bread and butter for many years here, with lots of applications in X-ray physics and elsewhere. So what this model looks like, you've got a linear mapping here. I split the space up into a product space, n-dimensional product space of d-dimensional subspaces, say. And this is a linear mapping. And so let's see, I'll look at this. The z hat is then going to be, each of the z sub j's are going to be these d-dimensional objects. And then the sets, the sphere type sets, are going to be these CJs, j going from 1 to n, say. And what we're doing is in each of these coordinates, we're specifying that this linear transformed variable has to have a certain magnitude, bij. And I might have j of these kinds of sets on this n-dimensional product space. And each of the j different sets would correspond to a different measurement with a different instrument or something like this. But they all have this characterization that the solution lies on some sphere relative to this norm. And we're in a Euclidean space, so let's say this is just the two ball. And then the cone is some qualitative constraint that's like non-negativity or support or something like that. And then my basic problem is I just want to find any point that lies in the intersection of these sets, presuming that this intersection is non-empty. But in fact, in almost every relevant application, this intersection is empty. So the question is, how do you deal with that? And so if we just look at the case where we just have two sets, a cone and then this sphere type set, the popular thing to do, the first thing I recommend anybody does is just alternating projections, cyclic projections. It's really easy to program, it's hard to beat, but sometimes it gets caught in local minima. So if that doesn't work, then I recommend to people is to try Douglas Rachford, which many of you know this. These R's, these are reflectors. It's 2 times the projector minus the identity. And then you average it's composition of reflectors across each of the sets with the identity. And the problem with that, though, you can use this as a test to see whether you have a inconsistent feasibility problem, because if you try to do this on an inconsistent feasibility problem, your algorithm will just go nowhere. It might diverge. It's a non-convex problem that probably won't diverge, but it'll just cycle around sort of chaotically. So then the next try is a relaxation of the Douglas-Rachford. And the relaxation, you notice the Douglas-Rachford part here, and then the relaxation is you just project onto the inner set, C1, to kind of anchor the iterates. And that usually converges. And so I want to give you an example of something. This is real data coming from the X-ray Physics Institute here in Göttingen. This data was produced by, it's an optical experiment, optical diffraction experiment produced by some undergrads. And what I was given by the professor here, he said, Russell, here's some data on the left. All I know is that the object lies in this yellow box. What's the object? So, well, the first thing I tried was alternating projections. This was the actual data was much bigger. I cut it off and made it a little bit smaller, just 128, each 128 pixels here. And now these are amplitude measurements. So the actual function, it's a complex value function, a real and an imaginary part. So the D dimensional thing, I'll just write that as the complex plane R2. And the model from the object where this yellow box is to the data is just a Fresnel transform. It's a fancy Fourier transform. And then my constraint was, he didn't say it was just any object in this box, but a real non-negative object. Okay. And then I ran alternating projections, and what I'm looking at here are the step size, the log of the step size here versus the iteration. I see something that looks like linear convergence here eventually. But if you look over here, the feasibility gap, I'm looking at the distance between the two constraint sets I have. This is going, the step size is going down 10 minus 10. Okay, that's looking like asymptotic regularity at least. And then the feasibility gap, however, is massive. This is a really inconsistent problem, even though my algorithm's converging. So, and I didn't like that picture. I said, oh, maybe this is a bad local minimum. So I'll try Douglas-Rachford. I should have known that Douglas-Rachford wasn't gonna work because of this gap, but do it anyway. And you do Douglas-Rachford, you get this red thing, and that's just as these are the steps. It's just cycling, and you can make a movie of this, and you'll just see this salt and pepper thing just move all around, and it's crazy. And the gap in Douglas-Rachford is going nowhere. This is just nonsense. So then I tried the relaxed Douglas-Rachford, and that's this yellow line, and that gives me the same answer that my alternating projections gave me, and this yellow is the graph there. So I achieved the same gap. Looks like slightly better asymptotic convergence, but now I want to explain these graphs and see if this is actually a solution. By the way, I sent this picture then back to Tim Zaldit in the physics lab, and he said, "Congratulations, you got it." So that's actually the answer. What it is a coffee cup, but you have to look really hard to see that. So the basic tools for understanding this behavior, this in vivo numerical behavior for real experimental data is there are two tools: metric subregularity. So this is I'm glad to follow on the previous talk, and almost alpha firm non-expansiveness. And this is a generalization of firm non-expansiveness that I'll explain in a bit. But what I'm going to try to tell you in the remaining 19 minutes is that if I apply my relaxed Douglas-Rachford algorithm to this situation, I've got my first set A is this ellipse in here, and it's just the boundary of this. And the second set B is this other ellipse out here. And if I start my relaxed Douglas-Rachford algorithm sort of in a neighborhood of this solution, or a neighborhood around here, I will converge eventually linearly to some point on this blue line, where which point I converge to depends on my relaxation parameter lambda. And I have to be careful. I can't choose lambda too close to 1, because the closer lambda gets to 1, the closer I'm going to Douglas-Rachford, and then Douglas-Rachford goes nowhere. There's no fixed point. You can prove that there's no fixed point for this. So just make sure that it's bigger than 1/2, because 1/2 takes me here. And so anyway, this is what I'm going to prove with the rest of the talk. By the way, together with Matt and Tao, we were able to prove that alternating projections converges locally linearly to, and their alternating projections would converge to this yellow point there. And we could prove that locally linearly. But if you think about all the theory that you know, most people everywhere on planet Earth, you would, there's no convexity here. Okay, scratch that. There's no intersection. Okay, scratch that. So we really had to develop new tools to deal with this. And as far as I know, the tools that we have are the only ones that are available for proving convergence of this, either in cyclic projections or for the relaxed Douglas-Rachford. So the abstract roadmap. we're gonna, because we're non-convex, our fixed point mapping is in general multi-valued. So we have a multi-value mapping from some subspace or subset lambda, subset of Euclidean space here, to itself. We have to assume that there exist fixed points here. And here, this psi is this residual mapping. We're looking at the residual of T. S delta, this is, I'm gonna blow a ball around the set of fixed points restricted to this lambda subset. And I would suppose for some ball around the fixed points that this residual mapping is metrically subregular for 0 on this kind of ambient space relative to lambda. So now what I'm using is relative to lambda is similar to what other people have been working with, like directional normal cones and things like that, to force them in directions where things are nice. This serves exactly the same purpose. And in my experience, the directions are usually anything kind of restricted to an affine subspace or a manifold where all of the action of the algorithm is happening. The second condition is, for some, that there exists some alpha between 0 and 1. Well, okay, so I'll give you the same. For all epsilon greater than 0, so this is kind of important because if I can verify 1 for some neighborhood, then if the second property, if I can always find an epsilon small enough such that my mapping T is pointwise, almost alpha firmly non-expansive at some point in the fixed points restricted to this subset lambda with average constant alpha and violation epsilon on this ball. Then, and I'll give you the definitions of these in a minute, but if you have these two ingredients, then for any point that you start in this subspace close enough to the fixed point sets, the sequence, the fixed point sequence, it converges to some point in the fixed point set restricted to this lambda, at least R linearly with a rate given by this. So you see how the constants of regularity here figure into the rate constant for convergence. Now here, implicitly, I'm really talking about linear metric subregularity. So in context of the previous talk, I could change this to a gauge and say that it's gauge metrically subregular. And then here, instead of a constant here, I would have some rate function actually, or a gauge here. And so if, however, in addition, if the fixed point set consists only of isolated points, then the convergence is Q linear, and we can get error estimates a posteriori and a priori. The logic of this setup is really inspired by a paper from Gurin, Polyak, and Reich, one of my favorite papers of all time from the late 60s. So really, I'm following the setup that they use and then just translating things into more the language of non-convex and inconsistent problems. So metric subregularity, we've seen this a bit through the conference. I've got Euclidean spaces here, but these can be metrics, just any general metric space. So I got a mapping from a multi-value mapping from one space to another, E to Y, and two subsets. These subsets don't have to be open, they can be closed, so that would allow me to isolate specific points. Then the mapping is called metrically regular with gauge mu, so this is the most general definition of it, on, now this is, it's defined on the graph really of this mapping, on U cross V relative to some subspace or some subset, as long as this inequality is satisfied. And if you look at this, what this is pointwise Lipschitz continuity, or non-linear Lipschitz continuity at Y of the inverse mapping of this psi. So as long as this inequality holds for all X in this neighborhood U, or this subset U restricted to lambda, and all Y in this subset V, and this gauge is positive here, and when this mu is just a linear function, then we have the usual linear metric regularity that most people are familiar with. And if in particular this set V is a single point, that's why I don't want these to be neighborhoods, they can be closed sets. If it's just a point, then we just call this metric subregularity. And that's the key thing, because metric subregularity is really the essential thing. And there are a lot of people who've worked with this for sure, and I'm not mentioning all of them. I'm just mentioning the ones that have had particular influence on my development of this. I'm not a developer of this theory. I'm a user of it. So in particular, I like Yopi. I'm using his formalism here. And then others, and also Klata and Kuma, that paper was really influential. And then Etienne and Terry's book. Alex and Tao and I wrote a math programming paper where we kind of, as everybody knows, this is deeply connected to all kinds of other notions, weak sharp minima, and KL property and all kinds of other things, and error bounds. So this really, but for me, this definition is the central organizing principle. Brief detour in a later paper with Marc Taboul and Tao, we show that if you have a fixed point sequence and you, for any fixed point sequence initialized anywhere on a neighborhood of the fixed points, if you have the property that will be linearly monotone with respect to the fixed points, that means that the fixed point operator, this residual, what I call the transport discrepancy, it's just the distance between your domain point and then its image. If that's metrically subregular for 0 on a neighborhood of the fixed point set, that's equivalent. So basically it says if you want a quantitative convergence estimate for some sequence, you have to have metric subregularity, which probably won't be a surprise to people in this crowd, but I'm talking often to applications people, and they hate metric subregularity. It's starting to catch on a little bit, but I've had to do a lot of work to kind of convince them that, yeah, it doesn't look very pleasant, but there's really no way around it. So back to the original motivation for this, I'm after explaining the yellow curve, and what we have here is numerical evidence based on this necessity statement. It says, okay, and I can do a numerical experiment and initialize my problem from anywhere, and I'll see a graph that looks exactly like this. So I have numerical evidence that there is metric subregularity happening here, and I just need to prove it for this. I already knew that I had the alpha firm non-expansiveness ahead of time, but it's the metric subregularity that's hard to get. Let's see. First of all, I'll explain what pointwise almost alpha firm non-expansiveness is. It is, so we got a set value mapping with some, if there exists an alpha and some epsilon here, such that this inequality holds for all x. Now it's all pointwise. This y is fixed, okay, but the x is varying on D for all elements in the image. That should be Tx there, and then for all elements in the image of y, this inequality. And the part that's key here is this psi here, because actually this turns out to be the exact thing that you need to be metrically subregular. But what this psi is this looks a little funny. I formulated this so that this works in metric spaces. But if you're in a Euclidean space, this simplifies to just the norm squared of the differences between the residuals at x and y. That's what that simplifies to. But if you're in a general metric space, you have to work with this messy looking thing. And also, if y is a fixed point, then in fact our multi-value mapping is single valued on its set of fixed points if it's alpha firmly non-expansive there. And this whole thing simplifies to just the difference between x and its image. So this, I'm just recalling our general map here to figure out how to prove convergence, linear convergence, the observed linear convergence of the method, and we just need to verify these 2 points. So the first one follows from, now there are ways to do this. You could try to calculate a coderivative. The people in the audience who think that's easy, I still am waiting to see somebody do that, but I have to go through subtransversality of the set. So I'm gonna take a different route and look at the regularity of the sets taken as a collection. Now, this is moving into the domain of Alex Kruger, who's studied this in depth. But But the key here is that these sets don't intersect. So I need a notion of subtransversality that works for that. And then, but the second property, this alpha firm non-expansiveness, this is going to come from regularity of the sets themselves. And that's, you can verify that. I mean, it's not always easy, but you can verify it. The first one is actually quite challenging. So just a brief history of this relaxed Douglas-Rachford algorithm. I proposed this back in 2005, where in the physics literature, it's called the RARE algorithm for, what's it called? Relaxed alternating averaged reflectors. And I did this precisely because the phase problem is inconsistent, and this was to stabilize another algorithm that the physicists really liked to use. But you can show that this is, you just take you relax the C0 set, that's a convex cone usually in most of the applications. So this is the nice set. The C1 is the non-convex set. So the algorithm corresponds to this optimization problem, in fact, for applying Douglas-Rachford, exactly Douglas-Rachford, to this problem. And you can show that this has fixed points, and you can characterize the fixed points in terms of best approximation points between C1 and C0. And so that's what I did in 2008. And then Robert Hesse and I were able to show convergence of Douglas-Rachford if the set of fixed points is strongly regular, or if the sets intersect strongly regularly, but where we had to require that one of them was an affine subspace or something. And then Hongfan was able to do that for general non-convex sets that are super regular with transversal intersection. And the transversal intersection, one more time, that's giving them the metric or giving us the metric subregularity that we need of the relevant object, and superregularity is just giving you the pointwise alpha firm non-expansiveness. Li and Peng in 2016 sort of rediscovered Douglas-Rachford, the relaxed Douglas-Rachford, and they were able to show a number of things that convergence of this in sort of in increasingly wild settings. So first, if it's convex and one of the sets is compact, they get this. If one of the sets is convex and the other is compact and both are semi-algebraic, they can get some rates. And if one of the sets is convex and at least one of the sets is compact and both are semi-algebraic. But the key thing is that they could, their rates and everything only work for non-empty intersection. And then Mindao and Hongfan have, in 2018, they showed R-linear convergence for superregular sets with linear regular intersection, and did a generalization of Douglas-Rachford, for which this is just one example of this. So first of all, this guy doesn't always have a non-empty intersection. In particular, if the sets are like this, you have one set, let's say the other, one set's the magenta on the outside, and then the other set is just a point in the middle. That the relaxed Douglas-Rachford algorithm doesn't have a fixed point. So you have to be careful. You still have to assume that the set of fixed points is non-empty. But the key, so together with Anna Martens in a paper that's been around for a while, but it just appeared in 2020 in SciOpt, we are able to provide sufficient regularity conditions, what we call super regularity at a distance. And this is slightly stronger than super regularity, which was first introduced in a paper with Adrian Lewis, myself, and Joel Malik. Super regularity is less regular than Prox regularity, but it's more regular than Clark regularity. And super regularity at a distance is somewhere between super regularity and Prox regularity. And the key issue here is that I need to characterize the regularity of the sets relative to a point that's not in the sets. Because my algorithm, my relaxed Douglas-Rachford algorithm is going to converge to this point x bar. And all of the regularity assumptions I have, pointwise alpha firm non-expansiveness and metric subregularity, are all going to have to be relative to a neighborhood of this point. But the regularity properties are going to be inherited by the sets that are somewhere else. So basically the whole the whole complication is involved in explaining how the regularity of these sets extends out away from the sets, and that's what this at a distance means. Okay, so but superregularity at a distance means that that we, for any epsilon, any violation of the usual firm non-expansiveness, you can find a neighborhood of the fixed point small enough such that the violation is arbitrarily small. Okay, so that's all. We in that paper also we were able to provide sufficient regularity conditions for subtransversality. Now, subtransversality of these two things, I'm quickly running out of time, so I'll have to really fly by those. But subtransversality of these two sets, this gets really complicated, and so we had to look at actually expand this to 4 sets. These 2 sets plus their images shifted by the gap. So it got quite involved. But basically, the way we were sure we had the right thing is that Anna went and came up with a way to show subtransversality, and we did not talk to each other, and I came up with another way. Mine had 3 sets that we worked through. Hers allowed for slightly more elegant results, so we kept with hers. But basically, it was that we came up with the same strategy led me to believe that this we've done it right. So superregularity at a distance, as I explained, there are a bunch of other notions of regularity of sets, and then basically, since these are projection algorithms, the question is, how does the regularity of the set, what does that mean in terms of regularity of its projection? Or the other way around, you could define the regularity of a set according to the regularity of its projection. So we've done a lot of work on this in the recent years, and it all kind of started with this paper with Jérôme and Adrian, and then recently Matt and Aristanalidis and I tried to then ask the question about functions, not just sets, in terms of the epigraphs of functions, not surprisingly. So superregularity at a distance, if you're interested, you can go look at the definitions of these. But the key point again is that the reference point doesn't have to be in the set. For the regular superregularity, it was only defined at points in the set. And as I mentioned, superregularity at a distance is stronger than superregularity. So, and then this, from this regularity notion of the set, we get the regularity of the projector and the regularity of the reflectors, and it's all in terms of these violations and how the violations then get passed on to our error estimates. Really quickly, the metric subregularity of this guy, as I mentioned, yeah, you can try to compute a coderivative of this operator and verify that it's injective for at points in the set of fixed points. That's an open challenge. I've been told that it's possible, but I'd like to see it. You need to calculate a coderivative of projectors. You need to calculate a coderivative of these reflectors, and these are resolvents and things. So it's complicated. Or you can go through a more geometric approach and look at this notion of subtransversality, as I mentioned, and our two original sets A and B. Then they have these twins shifted over in somewhere according to the gap and the direction, the order of the operations here. And so basically, what we do is we conclude metric subregularity of this mapping that is some sort of mapping measuring gaps between these sets. It's complicated. You can look in the paper with Anna Martens. we managed to get it and show subtransversality. And the key thing is that we're showing basic metric regularity of this mapping. This mapping is kind of a residual mapping, and the pi here is a permutation of our space. And again, this is totally crazy, but that Anna and I
Excuse
came
me,
into exactly the
Russell.
same way of doing this. I'm running out. Okay.
It's time
I
for
started
our
5
next
minutes late,
talk.
so. Yeah, I have to go teach my lecture anyway. So anyway, let me, we can put all these together and prove convergence of this. And so these are some of the papers that this was based on. So sorry, went over.
Thank you very much, Russell. Unfortunately, we have no time for questions. So we move to our next talk.